Okay, so last time we covered this section on diagonalizable groups and tori. So yeah, so let's just go over the highlights. So we start with the definition of a diagonalizable group. So this is a closed subgroup of a torus. So a torus being GM to some power. And then a closed subgroup of a torus is called a diagonalizable group. And the thing we showed was there's this dictionary. It's actually a contravariant equivalence of categories between diagonalizable groups and finitely generated abelian groups, where the tori correspond to the free cyclic groups. Products of the free cyclic group. And so the way we define this dictionary is by taking characters. So what were characters? So character is a homomorphism of algebraic groups from our group G to the multiplicative group. So in the TA session, you probably saw a different formulation of characters, equivalent, which is saying that these, the chi is a character if, as an element of the affine algebra, its coproduct satisfies a nice identity. So the coproduct is just chi tensor chi. So those are the characters of G. And a co-character is the kind of the dual notion. So it's a group homomorphism from the multiplicative group to our group. And we had this notation for the co-characters of G. And so, yeah, so as I mentioned, the characters live inside the affine algebra. And they're written as an abelian group additively. So this is a bit confusing. So the sum of the characters evaluated at G is the product of their values at G. And if G is commutative, then the co-characters are also an abelian group. Okay, so we saw some examples. So GM, so we did this, we proved this before, that the algebraic group homomorphisms from GM to itself are just given by the integers. And so its character lattice is just the integers. And then if we have a torus, then its characters are z to the n. We can write down nice bases. And similar, the co-characters are also z to the n. And we had this fact that the characters span, they span and they form a basis of the affine algebra. So any monomial in these chi's is another character. And the monomials span this Laurent polynomial algebra. So I think Shivi went over that in the TA session. So hopefully that's clear now. We had the co-characters, and then we had the finite group case. So the characters of a finite group, of a finite cyclic group, are basically itself, but the co-characters are trivial. So there are no interesting co-characters to finite groups. All right, and we had this important result that kind of characterizes diagonalizable groups. So a group is diagonalizable if and only if its a group of characters is a finitely generated abelian group, and the characters form a k-basis of the affine algebra. And that's equivalent to saying that any representation of G is a direct sum of one-dimensional representations. And yeah, as we saw, there was some facts that I needed to prove additionally to prove this theorem. So there's this theorem of Dedekind that the characters actually form a linear independent set inside the vector space of all functions from G to the field. And yeah, as was pointed out, this result is similar to something you see in finite groups. So if you have a finite abelian group, then any representation is one-dimensional, and if you're working over an algebraically closed field, any representation breaks down into irreducible representations, and each of those is one-dimensional. All right, so we had this result. So I sent an email to clarify this first part of the proof. A implies B. Hopefully that makes sense now. Then we had B implies C, which was maybe a bit opaque with these matrices A sub chi. But I think if you sit down and work through all the notation, it's fairly straightforward. So yeah, and then C implies A was pretty easy. Okay, so yeah, so as a kind of a quick consequence of this theorem, we see that when G is a diagonalizable group, then its affine algebra is just the group algebra of the characters. So then we talked about this construction. So starting with a finitely generated abelian group and producing a diagonalizable group, and that goes through the group algebra. So we first form the group algebra of the finitely generated abelian group, and then it carries a kind of a natural Hopf algebra structure, and then that Hopf algebra can be identified with the affine algebra of a linear algebraic group, and that's the group corresponding to M. Right. And yeah, so we had this stuff, and then the tori correspond to the z to the n's. So there was a question about why this is the case. Yeah, I think Shivi discussed that in more detail in the TA session. So it just comes from the construction, and I also sent an email about it. So we had that, and then there was this result about the rigidity of diagonalizable groups. So if we have a family of homomorphisms of algebraic groups from G to H, G and H both being diagonalizable, and we sort of, when we say family of group homomorphisms, we kind of formalize that by writing it as a map from V cross G to H, where V is some connected affine variety, and all if we fix our little v, then we get a group homomorphism like so. Okay, so the claim was that this family is actually the trivial family. There's only one real homomorphism from H to G going on here. There's not these different ones are all in fact the same. So yeah, so I gave kind of a sketch of the proof. Oh yeah, I still have this stuff here. So yeah, as I was saying something before, how we have a map from V to the characters of G, and since V is connected, this map must be taking everything to a point, and I guess that's technically true, but maybe a better way to think about it is that each one of these f psi sub chi's at little v is either 0 or 1. So in fact, it's more like we have a function from v to the set 0, 1. So it must be, and since v is connected, it must be constant. And we see that for any given psi, there's a unique chi where this is 1. So that means the function has to be constantly 1 at some particular chi that depends on psi, and it's 0 for all the other chi's given our psi. So that gives us, I guess that's what we have here, and that gives us the result. Yeah, so it's a bit maybe opaque, but it's not, yeah, it's not anything super sophisticated. So, and then as a result, we have this corollary that the connected component, so if we have a diagonalizable subgroup of any linear algebraic group, then the connected component of the normalizer of H coincides with the connected component of the centralizer of H, and this group is finite. Because if we just had the if we just had the connected component of, I guess you use the third isomorphism theorem or whatever here to see that this is finite. Because the index of the connected component of each of the normalizer and the centralizer is finite in the appropriate subgroup, and so then we get this. Okay, so and so one last thing. So if we restrict our attention to tori, so tori is being specific class of diagonalizable groups, then we get this perfect pairing between the character lattice and the co-character lattice. And this comes from just composition. So if we have a co-character, that's a map from GM to the torus. If we have a character, that's a map from the torus to GM. If we compose them, then we get a map from GM to GM. And this map, by map, I mean group homomorphism. And since these group homomorphisms are just given by an integer, we get an integer. So in other words, we have this identity for any element in the multiplicative group. And this is a perfect pairing. And the reason for that just comes down to the dot product. So because once we kind of pick bases, once we pick an identification of T with GM to the end, then this just becomes the dot product. And the dot product is a perfect pairing. All right, so that was the lecture from last week. Any questions? Anything anybody wants to ask about?
I have just one question.
Sure.
Why does it call tori? How is it related to tori?
Yeah, because so you're probably familiar with tori being you have the circle group in topology, and you have S1 to the n. And in topology, that's n torus. But here so that's the maximal compact. So basically, the relationship is taking the maximal compact subgroup. So in the theory of Lie groups, the tori, I guess the topological, let me call them topological tori, these S1 to the n. So those play the same role in the theory of Lie groups as these tori, these algebraic tori will play in the theory of linear algebraic groups.
Because the cycle, because the circle is homotopic equivalence to the plane without point.
Yeah, essentially that's that's kind of what's happening here.
The GM is the multiplicative, meaning in some way the rotation in axis. Here this is this. Okay, never mind.
Yeah. Okay. I think we'll see later on in the course how these tori play a role, and if you're familiar with the theory of Lie groups, you'll see that it's very similar. In fact, almost precisely analogous. Okay. Any other questions? All right, so let's go on to the new topic for today, which is derivations. So I guess I wrote derivations, differentials, and Lie algebras. For this PDF, it's only derivations and differentials. Lie algebras, well, maybe we'll get there at the end today, but I included those notes as a separate PDF. All right, so this is a bit of a slight change from what we've done so far. So maybe let me say a few words about what we've done in the class so far. So we imported a bunch of algebraic geometry. We gave the definition of an algebraic group and a linear algebraic group. And then the first important result was the embedding theorem. And then, so any linear algebraic group is a closed subgroup of GLN. And then we talked about the Jordan decomposition. And so we had the the result that any element in a linear algebraic group has a decomposition as the product of two commuting elements, one being semi-simple, the other one being unipotent. And then we explored some results about unipotent groups. And then we talked about commutative groups and one-dimensional groups. So there was a few results there. And then finally, last week, we talked about diagonalizable groups. So diagonalizable groups are commutative groups, and all their elements are semi-simple. So that's kind of on the other spectrum of unipotent groups. Okay, so now we're going to switch gears a little bit, and the goal is to associate a Lie algebra to any linear algebraic group. And to do that, we need some more objects and material from algebraic geometry. So that's what we're going to cover today. So this stuff is fairly basic. So I'm not going to prove everything, but I think most of the things, at least in the first few pages, can be deduced easily, and I'll try to point out which things are more sophisticated. Okay, so let's jump right in. So in this setting, R will be a commutative ring, and A will be an R algebra. M will be a Let module. For most of the time, we'll be assuming A is commutative. Some of these things work more generally if A is non-commutative. So, but if you just want to have A be commutative the whole time, that's totally fine. So an R derivation of A in M is an R linear map from A to M. So they're both R modules. This is an R linear map, and it satisfies the Leibniz identity. So if we take the product of two elements A and B inside our algebra, then the D sends this product to a sum of two things. So it's first of all, we have D of B. So this is an element in M. M is an A module, so we can act by little a. So we have D A times D of B. And then similarly, we can act by B on D of A, which is something that lives in M, the A module. So we have B times D of A. So it splits up in this way. So it's not, in particular, it's not a algebra homomorphism, but it's still an R linear map. So it's kind of a different sort of beast. And the notation that we'll use for R derivations is the following. So der sub R, A comma M. If R is clear from the context, then I'll sometimes drop the R, but that's a notation. So what's an example? Well, the easiest example and the kind of the motivating example is taking derivatives. So if let's say R is just our algebraically closed field and A is polynomials in one variable, then we have the derivative map. So that's an R linear map. So we don't need calculus to define it. We can just define it formally by on monomials. So t to the n goes to n t to the n minus 1. And this is a derivation because of the product rule, basically. But you don't need calculus. You can just check this. Check this on monomials, since everything is just algebraic. Okay, so that's kind of the one variable version. What if we have multiple variables? So what if our algebra A is polynomials in n variables, so the affine algebra of A to the n? Then each of the partial derivatives is a derivation. So for any I, we have a partial derivative map, and that's a derivation. It satisfies the Leibniz rule. Right. And so here are a few facts about derivation. So first of all, if we have an element in R, so A is an R algebra, so R lives inside of A. D is a derivation from A, so we can plug in elements of R into D, but all of those get sent to 0, and that's because D is R linear. So if you write R times 1, if you write R as R times 1 and you expand out using the Leibniz rule, then you'll see pretty quickly that D of R has to be equal to 0. And also, the other fact is that these derivations form a left A module, and that comes from the fact that M is a left A module. So these are just some linear maps that are valued in that are valued in M, and since A acts on M, it'll act on these linear maps. All right, and another fact, so how do these derivations interact with algebra homomorphisms? So if we had an R algebra homomorphism from A to B and the left B module N, then first of all, we can think of N as an A module where the action of A goes through this map phi. So the upshot is that we have an exact sequence as follows. So what's going on here? So this is fairly basic. So if we have a derivation, an A derivation from B to N, that's in particular an R derivation from B to N. So any A linear map is in particular R linear. So that's why we have an inclusion here. And then if we have a derivation from B to N, then we can just pull back, precompose, and get a derivation from A to N. So this is a map from B to N, so we can think of N sitting over here, B to N, and then we pull it back and we get a map from A to N. And the fact that phi is an algebra homomorphism means that the pullback of a derivation will again be a derivation. So we get a derivation from A to N. Right, and one special case of this is if phi happens to be surjective, then if we look at this term here, so if phi is surjective, then anything in B is in the image of A, and we know that A derivations have to, A derivations vanish on A, and anything, or on the image of A, and anything in B is in the image of A, so this has to be 0, so we get an inclusion here. So when this is an inclusion, then we can think of R derivations from B to N as a subspace of R derivations from A to N.
I have a question. Just
Sure.
is it a mistake or it's intentionally that there is no right arrow to 0?
It's not a mistake. It's intentional.
Okay.
So I think if the map is flat, then it's surjective, I believe, something like that. But I should double check. Okay. So then, so what's an example? So we said so we already talked about derivations from Ka to the n to Ka to the n. We said that we have these partial derivatives living inside here. And in fact, it's the free module generated by these partial derivatives. Yeah, so that's what's going on there. And if we, so now what about if we have some affine variety, some Zariski closed subset of A to the n? How do we describe, how do we talk about the derivations emanating from affine algebra? Well, let's suppose we're in that setting. So let's suppose that X is a vanishing set of some radical ideal. And so its affine algebra is the quotient of the affine algebra of AN by this ideal. So since the map from K brackets A to the n to K brackets X is surjective, then we get an inclusion of the derivations from the affine algebra of X to any module, I guess it's any K brackets X module, to derivations from the affine algebra, so this polynomial algebra, to that K brackets X module. So we can think of those as a subspace. All right, so kind of the motivating question that derivations will help answer is about tangent spaces. So you've seen tangent spaces in manifold theory. So, and there you rely on some sort of differential geometry. How can we do things just solely in terms of algebraic geometry? So in other words, more precisely, if we have a closed subset, Zariski closed subset of a to the n, and we have a point in that subspace, so in that affine variety, what is the tangent space? How do we define the tangent space of X at that point? So if we think about in terms of what the picture is, so if we kind of think about heuristically what the answer should be, we see that if we have our function, if we have, okay, so let me just read it. So if we have a vector in k to the n in this vector space, it's a tangent vector to x at little x. I claim that heuristically this is what should happen, that the dot product of the gradient for each function in the ideal defining x with this vector should be 0. So what's going on here? So let's consider the simple case where x is just given by cut out by some function. So I is a principal ideal generated by some f. So then if you think about it, so then the gradient will point in the direction that f is changing. But we want to know those directions where f is not changing as we take different level values of f. And those will be exactly the directions that are orthogonal to the gradient evaluated at little x. And so heuristically speaking, so this is kind of rough, but it can be made precise. So heuristically speaking, the tangent vector, the tangent space is all the vectors that have dot product 0 with the gradient. Okay, so let's take this equation and expand it out a little bit. So first of all, what's the gradient of f? Well, it's a column vector of all the partial derivatives of f evaluated at our point little x. And then v is a vector in k to the n, so it's just v, we have the vi's, and when we take the dot product, we just take the product of these two things. So yeah, so the partial derivative is a polynomial, some polynomial, and n variables, since we're in a to the n, and we evaluate it at x, and then we multiply by these v sub i's, and that sum of all these things should be 0 for any f in the defining ideal of x. So if we rearrange this a little bit, so we can just move things around. So we can think of these vi's as coefficients on the di's, on the partial derivatives. So now we have a linear combination of partial derivatives, and we apply that to f, and this is supposed to vanish at x. So that means that it belongs to the maximal ideal of functions vanishing at x, which I'm calling m tilde sub x here. So yeah, so we have this is just a rearrangement, and so what that means is that if we think of this linear combination of partial derivatives, then that's actually a derivation. That's a derivation from the affine algebra of a to the n to the affine algebra of a to the n, and but we know that any f, it kills any f that belongs to the ideal, so it factors through. So actually, sorry, let me rephrase that. So we have this derivation, and we can it lands in k brackets a to the n. Well, we can apply the quotient map and land in k sub x. So this is the one-dimensional representation of the affine algebra of either k brackets a to the n or k brackets x. And if we do this composition, then we know that it will vanish on everything in the ideal f. So that's why we get a derivation like so. And here, yeah, I mean, the notation maybe is a bit confusing, but m sub x would be the maximal ideal of k brackets x, defining little x, whereas m tilde was in k brackets a to the n. And so one direction is kind of clear, but then the other direction is also not too bad, because you can think about what these derivations are in terms of the derivations on k brackets a to the n. So in terms of that inclusion of derivations I mentioned just now, and yeah, and so we get this result. Well, this is just a heuristic, but it motivates the following definition. So the tangent space of an affine variety x at little x is defined as the space of derivations, k derivations from the affine algebra of x to the one-dimensional module k sub little x. So the heuristic that I outlined, it was kind of thinking about x as embedded inside of some a to the n, which we can always do for an affine variety. But this definition is just in terms of the affine algebra, so it's intrinsic definition for the tangent space. Okay, I hope that made some sense. Any questions about this definition?
How is this? Is this the same as risky tangent space? I mean, I've seen a definition that, for some reason, this is not the definition I've seen. It involved more like an analog of like Germ's modulo squares.
Yeah, it's equivalent. Yeah, we'll mention that definition in a bit. Yeah.
Okay.
Yeah, but that's exactly right. So for both derivations and Kähler differentials, we'll see that there's various different ways to define them, and they turn out to be equivalent. Yeah. Okay, any other questions? All right, so, okay, so now let's collect some facts about this new gadget that we've defined. So first of all, how does it, so actually, first of all, we note that we've only defined it for affine varieties. We'll get to the more general definition in a bit. So if we have a morphism of affine varieties, x to y, then we get a k-linear map from the tangent space of x at little x to the tangent space of y at the image of little x. So why is this? Well, it's just precomposition with the pullback map on the level of functions. So if we have something in here in this tangent space, then as we defined here, it's a derivation from k brackets x to the field, to this module. And if we, so, and then we have the pullback map that goes from k brackets y to k brackets x. So if we have a derivation, then we can just pull it back and we get a derivation from k brackets y to k brackets little x. But if you think about it, k brackets little x as a k brackets, sorry, k sub little x as a k brackets y module is the same as k sub phi of little x, if that makes sense. So I guess here this y is phi of x. Right, so this is, yeah, I realized after I wrote the notes, maybe I should elaborate here a little bit, but all that's going on is we just precompose with this pullback map, which is an algebra homomorphism, so it takes derivations. All right, so that's all that's going on there. And we also have the chain rule. So if we have morphisms x to y, and psi is a morphism from y to z, and they're all affine, then if we think about the differential of the composition at a point little x, then that's the same as the composition of the differentials. Yeah, so this equality of maps is linear maps from the tangent space at x, at little x, to the tangent space on the image of little x under the composition. And again, this is just writing out what, to verify this, you just write out what this differential means in terms of pullback along the map, the induced algebra homomorphism on the set of algebras. Okay. So now that we have those things, we can define the tangent space of a point in a general variety as the limit of the tangent spaces of if we have a point in a general variety, then we can think about all open affines in X that contain this point little x, and we can construct this limit. So the inclusion of various open affine sets induces maps on the level of tangent spaces, and so we can construct this limit, and that limit will give us this vector space, which is the tangent space at little x.
This would be isomorphic for different U, right?
Would they be isomorphic for different? Yeah, they would be, yeah, because all the U's are open and affine.
It ranges across all the U, no? What do you mean different for an U? It's the limit over all the open sets.
Yeah.
Then in X. Okay. Just an isomorphism class, not a.
Sorry, what? I didn't get it. What's
No, I just said that the limit is just isomorphism class. It's not some representation.
Well, it's a vector space. Like it satisfies the universal property. Yeah. So, okay. So, and the facts above about having induced differential maps and having the chain rule hold for non-affine varieties just as well. Okay, and so another fact, and this is just collecting some basic facts. So if this map of varieties is an open inclusion, then we just have an isomorphism on the level of tangent spaces for any x. And if it's a closed inclusion, then we have an injection on the level of tangent spaces. Okay, and so now I'm coming to these equivalent definitions of the tangent space at little x. So the first definition is as the dual space of m sub little x. So this is the maximal ideal of the affine algebra of consisting of functions that vanish at little x, mod it's squared. So germs of functions mod their squares, and this is the dual space. Why is that? Well, so I didn't write out the whole argument here, but the idea is the following. So if you have a derivation from k brackets x to k sub x, the fiber, then we can restrict that derivation to this ideal. And this is not a linear map, so it's not that this restriction is zero. Sorry, it's not an algebra homomorphism, so the restriction is not necessarily zero. But what we do know is that if we take anything in mx squared, then it has to be zero. And that comes from the Leibniz rule, because we will have something in mx acting on each component of the sum if you write out the Leibniz rule. So that's zero. So this restriction factors through mx mod mx squared, and we get a k-linear map. Like so, and then one must show that this is any derivation gives you, that this so what I've shown you here is a map from derivations to the dual of this vector space, but you can also go the other way, and so that's an equivalent definition. And the other equivalent definition is as derivations from the local ring at little x to k. So we define this ring of, I forgot what we called it, but it was the limit. If we had little x, then we had the limit of all the open sets containing little x, and we formed this ring, which is a local ring, so it has a unique maximal ideal, and k is the quotient. And if we think about all derivations from this local ring, to this quotient thought of as a module, then that's another definition for tangent space.
The
Yeah.
stock.
So sorry, the stock.
That the
Yeah.
word-
So it's this O sub little x that's the stock, and then this k is the fiber. So the mod the maximum ideal. Was that the question, or?
You're just looking for a word. I thought that was the word.
Oh yeah, I think in Springer there's a different word that was used, but yeah, that's stock works just as well. Okay, so those are the facts. All right. So any questions about this stuff with tangent spaces and derivations and differentials? All right. So now I'm gonna yeah. So let's define what smoothness means. So if we had if we have an algebraic variety, then we say, so then a point in that algebraic variety it's said to be smooth if the dimension of its tangent space is equal to the dimension of the variety. So maybe I should have said something like irreducible algebraic variety, so that the dimension is constant. So yeah, so if let X be an irreducible algebraic variety, then this makes sense. Let me just go ahead and add that in. And if we say that X is smooth, if it's smooth at all the points in X. Okay, so how do we, so let's see, what are some examples to get comfortable with? Well, a few lectures ago, I mentioned this variety, so the vanishing set of x squared plus y squared minus z squared inside of three-dimensional affine space, so K3. And I said that it's a cone and it's not smooth at the origin. So, and I didn't justify this, but now equipped with this definition, you can show that it's indeed not smooth at that point, but it's smooth at all the other points. And we had a somewhat related variety where the polynomial we considered had an extra constant, non-zero constant, might as well say it's 1. And this is smooth, this variety is smooth at all the points. Right, so that's that. And yeah, I guess the easiest way to check these things is actually to go back to, so since these are already embedded, you can go back to the thinking about the gradient and the orthogonal, the vectors that are orthogonal to the gradient at that point. And I think that's probably the easiest way to see that this is not smooth at 0, 0, 0, but this is smooth everywhere else. So yeah, so I'll let you think about that. So now I want to kind of import this kind of big theorem that I won't say anything about the proof. So what does it say? So let's say we have a irreducible variety of dimension D. Then the smooth points form a non-empty open subset of X. So so in some sense, generically, I'm hesitant to use the word generically because it could also mean something else, but generically, X is smooth. So if we pick a random point, then it's smooth. And in particular, we always have smooth points in X. They're dense. And the other fact is that the dimension of this tangent space at any point in X is at least is bigger than the dimension of X itself as an irreducible variety. So yeah, so I won't say anything about the proofs of these things. If You can look at the proof in Springer if you're familiar with scheme theory. Then there's kind of conceptually, there's another way to think about it, which is to show that, so if X is an irreducible scheme, that means it's affine algebra is integral domain. And so 0 is a prime ideal. So we have it defines the point in the spectrum. And you show that you can, there's still work to do, but you have to show that point is smooth, and then prove that smoothness is an open condition. So then that gives you that generically you would get open subset of smooth points in X. Okay, but yeah, I won't say too much about the proof of this theorem. So
if you mentioned like generic points, I wanted to ask if it's useful to like think about the tangent space at the generic point and think like things like that. Is this useful?
Yeah, definitely, yeah. So you need to be careful. The definition, yeah, maybe I don't want to say too much about it right now because it's a bit of a digression, but you need to modify the definition of tangent space. Or I guess you need to use one of the equivalent definitions that we gave, not the original one. And then that's kind of the first step, and you go from there. Yeah, does that help? Okay, so all this stuff was about kind of general algebraic varieties, and we want to relate these things to algebraic groups. So these things that I've defined now, how do they relate to algebraic groups? So first of all, as an easy corollary of this theorem, we have the following result. So if we have a connected algebraic group, so in particular, it's an irreducible variety. And here I believe we don't even need linear algebraic group, any algebraic group. Then we have the following two things. So first of all, any homogeneous space for G is smooth. So remember, homogeneous space just means G space with a transitive action. And G itself is a homogeneous space for itself under left or right multiplication. And so G itself is smooth. And a second, if we have a G equivariant map between homogeneous spaces, then it's constant rank. So the rank of the differential as a linear map between finite dimensional vector spaces is constant. It's the same for all X. Okay, so how do we prove this? Prove this corollary using the big hammer of this theorem that I stated. So there's since the set of smooth points in X is open and non-empty, then we can pick some point in X that's smooth. So X is a homogeneous G space. And if we have another point X prime in X, then since action is transitive, we can translate X to X prime with an element G. And the map on the level of tangent spaces is an isomorphism because its inverse is given by applying the inverse of G. So yeah, so in particular, they have the same dimension. And since X was a smooth point, that's equal to the dimension of X. So X prime is smooth.
Why is this an isomorphism?
Why is it? Because so it has you can think about it has an inverse. So if we do this map, the differential of the action of G inverse. By the way, maybe I'm abusing notation. I'm identifying G with the automorphism, associated automorphism on X. But then if we do this G inverse at X prime, then what we get is by the chain rule, that's the same as doing the identity on little x, and that's an isomorphism. That's the identity. So I guess it comes down to, yeah, the fact that if we have the identity map on a variety, algebraic variety, then the differential at all points is just the identity linear map. Right? Is that fine?
Yes.
So, okay, what about this second fact? So let me say the proof of the second fact and then we take a break. So let's take, okay, so the second fact says that it claims that if we have a G-equivariant map between homogeneous G spaces, then it's of constant rank. So let's take 2 points in the source in X, and so then we have these horizontal maps here at the top, and we want to show that they have the same rank. And since the action is transitive, we can pick a G so that G dot X is equal to X prime. And then the fact that phi is equivariant means that G applied to phi of X is equal to phi of X prime. And we have this commutative diagram. So, and since the action of G is by automorphisms, the induced map on tangent spaces is an isomorphism of vector spaces. Yeah, so I guess these are all facts that I didn't explicitly state, but are easy to show and match with your intuitions from differential geometry. Okay, and so since this diagram commutes, these two maps have, and these vertical maps are isomorphisms. The two horizontal maps have the same rank. So that's what we wanted to show. All right, does that make sense? All right, so let's take a 5-minute break and yeah, see you in a bit. All right, so where were we? Okay, so the next topic is Kähler differentials. So the setting is similar to what we had before. So R is a commutative ring, and now I want A to be a commutative R algebra. So A should be commutative from this point forward. So, all right, so we want to define the Kähler differentials. So what are these? So we first look at the multiplication map. So again, this is one definition, but there's various equivalent definitions. So I'm just following Springer here. So if we look at the multiplication map on A, so A tensor A over R to A, it has a kernel, which is an ideal I, and we define the Kähler differentials of A over R as the quotient of this ideal by its square, I mod I squared. Okay, so this maybe seems a bit bizarre, but we'll try to parse it and see why it's useful. So first of all, this ideal, if you think about it, it's generated by the following elements. So A tensor 1 minus 1 tensor A for any little a in the algebra. So it's clear that this is in the ideal since this goes to A minus A, which is 0 under the multiplication map. So in fact, I is generated by all these things. And by definition, the Kähler differentials are an A tensor A module. Why is that? Well, I is an ideal inside of A tensor A, so it's a tensor A module. And I squared is, again, living inside of A tensor A, and it's an A tensor A module. And so the quotient is an A tensor A module, but it has a natural induced structure of an A module. So why is that? Well, what do we need to, so I said, check this. What do you need to check? Well, it's, so a module for A tensor A becomes an A module if the action map factors through this multiplication map. In other words, if I act trivially on that module. And I will act trivially on this module I mod I squared, because if you act by I, then if you act by I on something in I, then you get it something in I squared, which is 0 in this module. So that's the explanation for why this the Kähler differentials, why those become a module for just for A. And we'll see another definition later on. So we regard omega A over R as an A module. All right, so then the other thing is, so I mentioned that these elements generate this ideal. That means these elements live inside of this module, or define elements of this module. So we're going to write dA for the image of A tensor 1 minus 1 tensor A, which lives in I, and its image inside of the Kähler differentials. So this is just notation, dA. And because these elements, A tensor 1 minus 1 tensor A, because they generate I, we see that the dAs generate omega A over R. Right. So, so in fact, we get a map from A to the Kähler differentials that just takes A to dA. And you can check that this is actually a derivation, an R derivation. So omega is an A module, and this is a map. So this is an R linear map, and you check that this is a derivation using the definition of dA. Right, and so the kind of the motivating, one of the motivating reasons to study these Kähler differentials is the following result. So if we have any A module, then we're interested in understanding the derivations from A to this A module. We saw that this has geometric significance in terms of tangent spaces and so forth. But the derivation condition is maybe a bit hard to work with. So it's much nicer if we can say that these are actually some sort of A linear maps. And in fact, that's true. And these are the same as A linear maps from the Kähler differentials to the module M. So these are just two A modules. We just take the A module maps between these two A modules. And the claim is that that's the same as the derivations from A to M. And the map is given by precomposition with this map D. So up here we had this map D. Maybe I should have written D here. So if we have a linear map, then we can produce a derivation by first applying D and then applying the linear map. It's easy to see that that's derivation. Okay, so why is this an isomorphism of A modules? Before we show the proof of the theorem, just to point out, so we can think of this a bit more categorically. So we have this functor that's taking derivations, so that maps an A module to its derivations. And this theorem shows that this functor is representable, and the representing object is the modular Kähler differentials. So that's what's happening here. If this sort of jargon doesn't make sense to you, then ignore it. It's not important for this class. So how do we see the theorem? Well, first of all, okay, so we go back. So I guess capital phi is the notation for this map. So first of all, it's easy to show that it lands in derivation. So because D itself was a derivation, this composition will be a derivation. It's also easy to check that it commutes with the A action because the A action is just on this M on both sides. So that's that. And it's injective because D is injective. I guess that's something maybe to argue that D is injective, but it's easy to see from the definitions. So the only maybe mildly tricky thing is to show that it's surjective. So let's take something in the derivations from A to M, and we want to define a linear map from the Kähler differentials to M such that the capital phi applied to that linear map is D. Okay, so first of all, let's consider this map psi. So this map psi goes from A tensor A to M, and it takes A tensor B to be B acting on D of A. So D of A is something in M, we act on it by B. So this map is kind of strange, but it turns out to have some nice properties. So first of all, it's R linear. I guess that's not hard to show. And second, so this is maybe a bit not as immediate, is that if we have two elements in A tensor A, then if we do psi, then we have the following identity. So psi of the product is well, first we multiply out x. So x is like a 2 tensor, so we can multiply it out to get something in A, and we act with that on the element of M given by psi of y. So that's using the definition of psi, and then we add the same thing but with the rows of x and y reversed. So this seems kind of weird, but it's easy to prove when we have just simple tensors. So x is A1 tensor B1, y is A2 tensor B2. So if you write it out, then you'll see that this is true, and yeah, and it extends by linearity. So once we have that, we can deduce that psi vanishes on I squared. Why is that? Well, I is the kernel of M. So if we had something in I squared, so let's say x and y are both in I. So then xy is in I squared, and anything in I squared is of this form. And when we apply this formula here, we see that we have m of x appearing and m of y appearing, but x and y are, if they're both in I is the kernel of m, so both of these are 0, so the whole thing is 0. So that's why when we restrict psi to I, it factors through I mod I squared. So that's why we get a linear map from that's how we get this linear map from the Kähler differentials to M. And it's an A linear map, and it's, yeah, if we precompose by D, then just following the definitions, we get that we get the original derivation D that appeared in the definition here of psi. That's how we'll recover it. Yeah, and yeah, I guess for the last, just one little note for the last part, you can just check it on these elements, A tensor 1 minus 1 tensor A mod I squared. Yeah, so that's the first important results about Kähler differentials is that they represent derivations. Derivations are just linear maps out of the Kähler differentials. Right, okay. If there are no questions about the theorem, then let me move on. So we saw above that there was a nice interaction with derivations when we had algebra homomorphisms. So what happens with Kähler differentials? Well, the map goes the same way. So when we have our algebra homomorphism from A to B, then we get a map of A modules from the Kähler differentials of A over R to the Kähler differentials of B over R. And it's so this diagram commutes. I guess this should be phi superscript 0. So we get this, this map of A modules. Okay, so this was all kind of abstract. We'll be concerned about these ideas in the context of affine algebras, so things that are finitely generated over ring or a field. So the important thing to understand is how these things work in the context of polynomial rings. So let's say that our algebra A is the polynomial ring over R in n variables, and let's say we have a module for this polynomial algebra. Then the claim is that there's the following isomorphism. Then and this isomorphism is as, I guess it's A modules, so as modules for this polynomial ring. So there's an isomorphism from n copies of M to derivations, R derivations from the polynomial algebra to M. And maybe in some sense, maybe this is clear from the fact that I said before that derivations are a free module with basis given by the partial derivatives, but it's useful in terms of computing things to have a more explicit form for this. So how does this work? Well, if you take something in this direct sum of M, n copies, so M sub i's, then we can define a derivation that takes a polynomial f. You do the partial derivative you do the partial derivative of f, and then you let it act on M sub I. So that's coming from the module structure, and then you take the sum of all these things. So again, d sub I is just the partial derivative with respect to t sub I. So yeah, so as I said before, this is just a reformulation of this fact that derivations have this nice structure. So you can compute that this is in fact a derivation. That's clear because we have these derivations given by partial derivatives, and to see that it's also clear that it's injective. To see that it's surjective, we can use the inverse map, and the inverse map is given by the following thing. So if we have any derivation from this polynomial algebra to M, then we can just look at where all the generators go. So we have the generators T1 through Tn. We can look at where they go inside of M, and that determines everything. Because we can get anything else. So any element in R is built out of the generators, except to define a derivation, it's so both to define a derivation and say R modulo homomorphism or R algebra homomorphism, it's enough to specify things on the generators, except with an R algebra homomorphism, you extend using the fact that it preserves products, but here you extend using derivations. Yeah. So that's the idea. So if we have a derivation, if we look at where these Ti goes, that determines everything else, just by the Leibniz rule. Okay, so yeah, so these things can be a bit confusing with all the notation and everything, but it's not super difficult conceptually. So, okay, let's okay, so now we get to an important proposition that allows us to compute things. So let's say we have a finally generated R algebra. So it's a quotient of some polynomial ring over R, and we want to compute what the Kähler differentials of A over R are. So the way to compute them is as follows. So the claim is that there's a surjective map from A to the N to the Kähler differentials. So N is the number of variables in this polynomial algebra that surjects onto A. So it's the size of a generating set for A as an algebra. And we take the free module, the N copies, the free A module generated by some elements. I'm just going to call them E sub I. So these are just some elements. We take the free module generated by those. Or you can think of E sub I as being the element that has 1 in the ith copy and 0 everywhere else. That's the standard basis of a to the n. Okay, so that's just explaining all this notation here. And this map to the Kähler differentials takes this E sub I to the following thing. So we take T sub I here, we map it, we think of it as an element in A, so we get pi of T sub I. And then we do little d. So d takes us from A to the Kähler differentials. And the claim is that this map is surjective. Actually, that's not hard to see. That's not the real content. The real content here is describing what the kernel is. So the kernel is an A submodule, and it's generated by the following things. So for it's generated by the following expressions for f inside the kernel of pi. So you can think of f as like you can think of the kernel of pi as like the defining ideal for A. And for any f, we have the following elements. So we do the partial derivative of f. We do pi, so we just think of it as an element in A. And then we put this in the ith factor of the free module. And then we take the sum over all the factors. And this if we take this submodule where f ranges over everything in the kernel, then we get the kernel of this map, surjective map. So then the Kähler differentials are a to the n mod this submodule. Okay, hope the proposition makes sense. I know it's kind of confusing, but it does really help when computing things. All right, so how does this work? How does the proof work? So let's just give this submodule a name. Let's call it K. And what we want to show is that there's that anytime we have, so we want to use the universal property of the Kähler differential. So we want to use this characterization of Kähler differentials as representing derivations. So what we want to show is that this, if we take an mod this k, then that also has this universal property for Kähler differentials as a representing object for derivations, and then that'll allow us to conclude that they're actually the same. All right, so we want to we claim that there's we get an induced map like so that fits into the following diagram. So first of all, M is a module for A. So I don't know if I said this here anyway, but maybe it's understood. So N is a module for A. In particular, it's a module for the polynomial algebra because A is a quotient of the polynomial algebra. So we had this from the previous lemma, we had this isomorphism phi from n copies of M to derivations from the polynomial algebra to M. And now any homomorphism from AN, so forget about K, AN to M, that's just an n tuple of things in M. But if we have something in a hom from this quotient to M, that's an m tuple of things an n tuple of things in M that satisfy certain property, that satisfy a certain condition that tells us that that this kernel acts trivially, basically. So there's an inclusion here, and there's also an inclusion here. That's because of this fact that I stated at the beginning, that if we have a quotient of algebras, an algebra homomorphism that's surjective, then we have this inclusion of derivations. Okay, so we want to see that there's a induced map here. So why is there an induced map? So let's take n tuple in M direct sum n times. Then we can define a homomorphism from the free module from AN to M just by taking each of these EIs to MI, and we can we can see that this homomorphism factors through the quotient if and only if the following condition holds. So this is just the definition of K. K is the thing generated by all the things of this form, almost of this form, except now we want to go to M, so we replace the EIs by MIs. So if this identity holds for our n tuple, then we get a map from the from this quotient. And this has to hold for everything in the kernel of pi. So the defining ideal of A. All right. On the other hand, let's think about this n tuple and let's map it via phi to give us a derivation. So it's a priori it's a derivation just from the polynomial algebra to M, and we claim so it just lands in here. When does it actually land in derivations from A to M? Well, it lands in derivations if and only if it vanishes on all the things in the kernel. So A is a quotient of our T1 through Tn of the polynomial algebra, and a derivation from the polynomial algebra to M factors through A if and only if it acts as 0 on all the things in the kernel of the quotient map. Okay, so what does it mean to be acting by 0? Well, we have to rewrite, so we use the definition of this phi. So the definition of this phi means that the partial derivatives, we need that the partial derivatives of f acting on m sub I are 0 for all the f's in the kernel. So you can go back and kind of think through this, or you can kind of think directly why this should be the case. And then it's just a matter of notation here. So if the action of these polynomials is technically speaking factors through pi, so the action, the polynomial algebra is through the quotient map pi to A, and so we just put a pi here for notational reasons. And so we see that we have the same condition, both for this tuple to be defining a homomorphism from the quotient to M, and so a module map from the quotient to M, and the derivation from A to M. So that means that we have this this isomorphism, and yeah, so this basically implies the result. So you can since I'm just going to say universal properties, Yoneda lemma, if you prefer. This implies the result. You can also go through and check it concretely. Okay, so I know that was maybe a bit technical, but it'll actually be very useful to have this lemma around, or this proposition around. Any questions on this proposition and the proof? All right, so if not, let's, one more remark. So the, when actually computing this, it's enough just to think about generators. So you can, this submodule that we have to quotient out by, it's by definition, it's some equation, some condition on all the elements in an ideal. But we can just take a generating set for the ideal and check and impose the condition coming from the generators. So yeah, so that's just a remark. Okay, so now I said that this will be useful for computations, and also we need to relate things back to algebraic groups, since this is a course on algebraic groups. So let's use this proposition to compute the tangent space at the identity of the group SL2. So yeah, so how does this work? So I know most of you probably already know what the answer is, but let's pretend we didn't know what the answer is, and let's just use algebraic geometry to figure it out. Okay, so by definition, the tangent space is all the derivations from the affine algebra of SL2 to K sub 1. So this is the fiber at 1, which is a module for this affine algebra, quotient by the maximal ideal, of course, the corresponding maximal ideal. And then we can write this in terms of Kähler differentials. So these are the linear maps, the K brackets SO2 linear maps from the Kähler differentials to K1. I omitted the notation over K here. So to be pedantic, it's Kähler differentials of this ring over the field K, just like I omitted the K here in derivations. So just to recall, the affine algebra of SO2 has 4 generators, and there's a single relation. So it's a quotient of the polynomial algebra by a principal ideal, AD minus BC is equal to 1, or I guess maybe it would have been better to write AD minus BC minus 1. And the action on K1 is just given by the co-unit map. So if we want to be explicit, then if we have a lambda in K1, so it's just the element in the field, then A and D both act as 1. Oh, this should be a lambda, not a 1. The action of D is by 1. And B and C act by 0. So that's clear from what the co-unit map is doing. And it's clear because it's coming from the identity matrix in SO2. Okay, so we have so these are just notational recollections. So the claim is that the Kähler differentials of SO2 is the free module. So I wrote it in symbols and in words here. So it's the free module on four elements mod this this relation, mod the submodule generated by this element. Yeah, so as you might expect, the way you prove, so this looks kind of maybe a bit unexpected if this is the first time you're seeing it, but it's easily explained, as we'll see now. So how does this work? So as you might expect from the notation, we will just use the lemma from above. So we know that there's a quotient map from the polynomial algebra in 4 variables to the affine algebra of SL2. And yeah, I'm just going to abuse notation a little bit and just use the same symbols so yeah, I'll try to be clear when, for example, little a denotes something in the polynomial ring and when it denotes something in the affine algebra of SL2, but hopefully it'll be clear. So yeah, so we have this quotient map. So using the lemma, or maybe it was actually a proposition from above, we have to compute. So this tells us that the fact that we have this quotient map tells us that the differentials, the Kähler differentials, are a quotient of the free module on the appropriate number of generators. We just have to compute what the kernel of that map we had is, what that submodule we quotient by is. And we had a very explicit description of that submodule. And in order to apply that explicit description, we need to compute these guys. So there's only one F here. So we just have one generator. This is our F. And we need to compute the partial derivatives. And then we need to have them, those would be the coefficients and the EIs. So here I wrote it with I's to make it consistent with the proposition from above, but E1 is just EA, and then E2 is EB, and so forth. Okay, so we need to compute what this is. So by definition, we have to do all the partial derivatives and have the appropriate, those would be the coefficients on the E's. So we compute each of these partial derivatives. So what's the partial derivative of our f with respect to a? Well, it's just d, because the partial derivative of a times d is just d, and the partial derivative of b, c, and 1, those are both 0. And similarly, we get a c with the eb, a b with the ec with minus signs, and an a with the ed. So that's, yeah, just basic stuff. So that's what this element is, and that by the proposition above, that's the only thing we need to mod out by to get the Kähler differentials. Okay, so yeah, that's that. I guess maybe maybe it takes some time to internalize these sorts of computations, but that's what we get. So finally, we can compute what the tangent space is. So we need to compute the harms from the Kähler differentials. So this was what we just convinced ourselves of, to K1. So what is that going to be? Well, this is the quotient of a free module. So it's determined, so any linear map is determined by where EA, EB, EC, and ED go. So that's what I'm calling their images here. They have just with the bars. So EA goes to some element in K. So K1 is just one-dimensional. So we identified it with the field. And EB goes to some EB bar and so forth. But we can't choose them any way we want. We have to impose this condition. And this condition tells us that D acting on this scalar E bar A minus C acting on the scalar E bar B minus B acting on the scalar E bar C plus A acting on the scalar E bar D, that has to be 0. Well, we already know what the action, so above I reminded you what the action of these generators is on K1. So in particular, C and B both act by 0, so those disappear. And A and D both act as the identity. So we just get E bar A and E bar D is equal to 0. So we can think about these as 2 by 2 matrices where the trace is equal to 0. So at this point, it's not clear why it's useful to formulate this in terms of 2 by 2 matrices, but in the next lecture on the algebras, we'll see that this is the right thing to do. Yeah, so there we go. We computed the tangent space at the identity of SL2. And maybe, so similarly, a nice kind of, if you like this sort of computation, or if you want to get better at these sorts of ideas, you can compute what the tangent space at the identity of ON is, and you see, so ON is orthogonal matrices, so matrices whose, when you multiply by its transpose, you get the identity matrix. And the tangent space can be identified with matrices such that if you take the sum with the transpose, you get 0. And if you kind of proceed along the same lines that we just did with SL2, then it should be fairly clear. Maybe I'll ask Shivi to go over this computation in the TA session. Okay, so that's it for today. I finished this PDF. Yeah, are there any questions? Shivi?
Yeah.
So is it okay if you go over this example in the TA session? Okay, cool, thanks. All right, well, if there are no questions, then I guess we can, let me stop the recording.